Kepler's Laws of Motion. In this video we'll be talking about Kepler's laws of planetary motion. Now there's a lot on the slide, but there's only 3 laws. So Kepler was a German mathematician who came up with the laws of planetary motion in early 1600s. Now you can imagine the patience that he had when he was observing the planet Mars without the technology that we have today. So Kepler's laws describe specifically the motion of the planets around our sun. From that, they can also predict the motion of stars, moons, other satellites and comets around the universe. Kepler's First Law states that planets move in elliptical orbits with the sun at a focus. Now, observing these diagrams, we have to make note of a few of the new definitions that we see here. So first, we've got the 2 foci of an ellipse. And you can compare the foci to the radius of a circle, but with an ellipse, there's 2 of them being in the shape that it is. The 2 other important points are the perigee and the apogee. Perigee is the point where the moon is closest to the Earth, and apogee is when it's furthest away. And linking that to the Earth's position relative to the sun, we have the words aphelion and perihelion, where aphelion is the position where the Earth is furthest from the sun, and perihelion is where the Earth is closest to the sun. Kepler's second law states that as a planet orbits the sun, a line from the sun to the planet sweeps equal areas in equal intervals of time. So observing this diagram, you can see that this area here is equal to this area here. Even though the planet is closer to the sun at this point, it travels a lot faster. Compared to where the planet is furthest from the sun, it travels a lot slower. Kepler's third law of planetary motion states the orbital period of a planet depends on the average distance from the sun. So according to this formula, the period squared is directly proportional to the average radius or the average distance from the sun cubed. And although we're talking about distance, we use r because it is in that circular or elliptical shape. Alright, so now we're going to have a look at the derivation for this formula. So we start by having a look at the velocity of an object in a circular path, being the distance over time, and because we're looking at the orbit of a planet, the distance is the circumference of the circle, and the time is its period of 1 lap. Okay, we're going to substitute v with the value of the square root of gm over r, and this is related to Newton's second law and acceleration, but this one's on your formula sheet. Now with a bit of manipulation, we square both sides, evaluate the right hand side, and then just rearrange for period, and we can achieve this equation. Although what you see on the screen is a derivation just mathematically, if you're required to do this in a test or the exam, a little bit of explanation of why these values were used. So this being the velocity of a particle in a circle, and substituting here is the velocity based on the gravitational constant, the mass of the sun or the planet, and the distance away that it is. This equating will require one line to explain why the equations were used. So the question for this video is to draw a diagram of Earth's orbit around the sun, labeling the aphelion, perihelion and the foci, and then as an extra challenge, do the same for the moon's orbit around the Earth.